thermodynamics. As I early make some story, first of all, we have to give some crystal preparation, giving some coordinates of atoms. In our case, we are going to take some metals. Those are the D block elements, and those are actually all maximum have FCC lattice with the coordinates, and at 0 Kelvin we give some coordinates, and then we will give some velocity initializations by a Boltzmann distribution, which is given over here, and then integrate the classical equations of motions by Nordsig algorithm. This is actually the computer program algorithm which have a time step of 10 to the minus 15 second in femtoseconds, and carry all the types of the equations over there to calculate the Hamiltonians, energies, potentials, and forces among the potentials among the atoms. Then keep in mind we are going to do with on the computer, and we cannot take the infinite crystal, so that we have to introduce some periodic boundary conditions. We are going to take some supercell, maybe of 2400 atoms, maybe 2000 atoms. But in real, you people know that if we consider a tip, a point, millions of atoms are over there.
Slides,
So we have to produce.
Sorry to interrupt you, sir.
Yes.
स्लाइड तो चल रही है, पर किसी के पास कोई मसला है? इट्स ओके सर, कैरी ऑन सर. ओके जी सर, डॉक्टर साहब बस कैरी ऑन सर.
To make the things just like real things, we have to give some periodic boundary conditions, and then I will explain the periodic boundary condition in next slides. Then we have to minimize the energy of the configurations, and just like the optimization of the system, then equilibrate the system. Then further we can start the other calculations. This is the periodic boundary condition. How this is? Let's suppose we have taken this type of supercell, and this is now in reality we have to give some infinite positions of atoms. What we have to do? We have to give some periodic boundary conditions in 3 dimensions, just like by producing some image in such a way that the left one atoms are interacting with the right one, and the upper one interacting with the lower one, and so on. In 3 dimensions, if we have some defect, it will reproduce in such a way. We can see over here that the yellow color ball and the red color balls are repeating. On the other side, if we have some defect, it means the defect is going to repeat. While we have achieved that the boundary effects are going to reduce, surface effects are going to reduce, because we have taken the images repeating in 3 dimensions. This is just like unphysical, but in computer we can do. Now this is the story how it means this yellow ball atom is not interacting with this is the lattice constant, but it is interacting actually with the other unit, which is the image of this one. We can say that this is the length of the atom. The supercell is just like the lower line, which is horizontally representing that. To make the infinite system, the number of atoms that we have to consider during the simulation is determined by the number of atoms of the simulation cell. The distance between the atom I and j is defined as the distance between atom I and the closest image of the atom j, which I previously described. Now this is the we take the potential cutoff, which is the R cut actually. Now at the minimum level we have to make the story in such a way that it will complete this spherical ball in such a way by reproducing the image in 3 dimensions, and these will be completed by the periodic boundary conditions. The atoms are interacting with their own images, totally unphysical, as I said. While in computational, this is we have to do only if L greater than 2RC, we automatically satisfy the conditions, set minimum image conditions. Every particle I interacts at most with the closest image of the particle J, and these are the actually things we can see. Though let's suppose we have a supercell. for the purpose of to creating surface, we have to give the periodic boundary conditions in 2 dimensions, while which is the surface required. In that direction we have to give some fixed boundaries so that image art is developed in that direction. No, during the simulation, actually, this is the molecular dynamics, and we are going to focus on the dynamics of the or oscillations of the atoms. We have to take the time step of the in such a way to all calculations to do the huge programming which is behind the story. Uh, in case of equipartition theory, between working behind the story and the conjugate gradient approximations are working behind the story. We have to take the time step in such a way that our atomic oscillations can be recorded. If the characteristic period of the time tau is in such a way that delta t less than tau, tau actually representing here the atomic oscillations, and we have idea about atomic oscillations in the form of, we can say that the period of the atomic oscillation are in 10 is to minus 12 to 10 is to minus 10 is to minus 12 to minus 10 to minus 13 second. We have to take the time step less than this one. That's why we taken over here in Nordic algorithm in femtoseconds to catch those events, to catch those oscillations which are occurring over there in the molecular dynamics. There are 3 types of the ensembles which are going to use over here. First is the NV ensemble, which is microcanonical with conjugate gradient method to minimize the structure or optimize the structure for the relaxation, and NVT canonical ensemble, which is to use to thermalize or equilibrate the system, to shake the systems. On the other side, NPT isobaric isothermal ensemble, which will be used for to attain the temperature for the simulations, and while for to see the long run or to see the dynamics which will be evaluated with the passage of time, can be seen with the NV ensemble. Now, first of all, energy minimization by conjugate gradient method. There are left side actually representing the two photos, one with the steepest descent approach, and other one is the conjugate gradient method, lower one. This is the optimization way to relax the structures on the surfaces. Actually, atoms just relax towards the inside the bulk, and the way how crystal as a whole relaxed can be seen here. And the right one, it takes some attempts again and again in number of 600 plus iterations. The energy of the crystal becomes ideally constant, and we minimize the structure by the conjugate gradient method. Energy of the crystal here along the y-axis, and at 700 Kelvin actually this is the process. And for copper 11, we increasing the number of iterations after a perpendicular cut, the value of energy becomes constant. The surfaces relaxed, here we have seen that the relaxed and unrelaxed surfaces for copper 11, copper 31, copper 210, these are the values for the relaxed and unrelaxed. We have seen that there are a little bit difference on the surfaces, while in bulk there is no relatively or we can say that there is no noticeable differences inside the bulk. This is only appreciable at the surfaces. NVT simulation, this is the pattern for the 10 picoseconds at 900 Kelvin, temperature versus time. We can see that this is the how it makes the system to equilibrate and how it is going to reduce the noise. It requires actually 20 picosecond. It is I given over here just for 10 picosecond. That's why it's a little bit remains some noise to confirm the system thermalized. We have to give some 20 picoseconds. This is the NPT ensemble to raise the temperature, and this is how we came from 600 to 300 Kelvin. And this is the first of from left to right. This is there is some major fluctuation, then it's going to decrease, and so on. However, small fluctuations will remain over there. This is actually how we can do the isothermal isobaric simulations at a specific temperature. We can say that on the other side, to attain temperature to to do the simulations. Now, simple statistical quantities which we can measure during the molecular dynamics, which we have to face. Let's suppose we have a generic physical property A, which is the function of velocity and the positions at any time t. We have to take some averages of that physical quantity, and we can, if we have position coordinates, and then we can calculate the average potential energy, which is the function of position. We can calculate the average kinetic energy, and we can calculate the total energy. We can find the temperature by equipartition formula. We can calculate the mean square displacements and the diffusion coefficients. This is the empty flow diagram. We have, first of all, we have to give some initial coordinates, then we assign velocities, then we have to do some Newtonian equations. We have to solve some equations. Then after that, we have to minimize the structure to equilibrate the structure. We can say that the optimize the structure. And if there is some equilibration, there is some problem, we have to again and again make some iterations, and then we have to do some products dynamics. We can record some statistics. We can further to do raw data to do the other required physical quantities and so on. Some examples of the applications. This is the lattice parameter of the silver. Comparison between the simulated and experimental values. Lattice parameter we have seen over there for the silver, which is very closer to the experimental ones, and we compared with the Clinters et al. Also, we have seen that that guy actually given the values with using the tight binding potential, and the difference between the calculated and experimental values was very small. Those were in the 0.75%. We can say that 0.0031 nanometer are higher, while on the other side the trends are same. Why these values of experiment are a little bit low as compared to the calculated values? The reason behind the story is that the calculated values which we done over here, actually these are the ideal crystals. On the other side, experimentally there are some defects are available, and that's why a little bit lattice parameter changes. However, the trends are same. We can say that this is very near to the experimental ones. These are the snapshots of the copper pentamer diffusion. Keep in mind, these spherical balls are representing the atoms, and blue color atoms are actually representing the silver atoms, and the red colored atoms are actually the copper atoms. These are adsorbed on the surfaces. These are not the part of the crystal. And we increase the temperature, and we saw the with the increase of the temperature, we saw these red colored atoms changing their positions during the simulation. We saw some photographs which are representing over here. There are nice photos of the copper atoms, and this is the same. We can think just like we old fashioned ladies. They always separating the chaff with the from the wheat. They just vibrating the substrate while the things are going to separate. These are just like our threshers of wheat. They are separating after there is not pulling in specific direction. This is the vibration of the substrate, and the upper atoms getting some dynamics from the lower atoms, and they are going to change position because these are not the part of the crystal. Actually, they are all absorbed on the surface, while on the other side the atoms of the crystal, they are bounded. They cannot leave from the surface, while these atoms can change their positions, and that's why we can say that they are diffused, two-dimensionally diffused. This is the surface diffusion, and we have seen the last peak. There is pop-up of an atom. One atom becomes popped up over the other four atoms. This is the pentamer island on the surface, and we saw here very nice and beautiful pictures of the during the surface diffusion. This is the center mass of the pentamer on silver vermilion. Variation of this island, which is the pentamer, with the time we have seen that in the left one is at 500 Kelvin, while on the other side this is the at 700 Kelvin. We saw over here that the variation in the center mass at high temperatures is relatively more as compared to the lower one, and this is the function of actually time, and we can also see with the change in positions just like a movie. I will show you in the next slide maybe. This is the RNS plot. We calculated actually the center of mass, MSD, then the diffusion coefficients. RNS plot actually here of the diffusion coefficient of copper pentamer. This is the diffusion coefficient formula here, and the RNS plot actually providing some. So we can calculate the energy, excitation energy barriers from the slope of that one, and the inset displays the mean square displacements for the pentamer cluster on silver 11 as a function of time at 300, 500, and the 700 kelvins. These are the trajectories of the center of mass. This is the 7 copper atoms on the copper 11 surface, and the 7 silver atoms on the silver 11, and the next one the copper on the silver one. We can see that with the increase of the temperature, this is actually the trajectory of the island at 400, 550, and the 700 Kelvin. You can see that with the increase of the temperature, the trajectory shows that the major part as a black because it moves enough. And we can make some comparison in case of the copper and the silver clusters. We can say that the silver's dynamics are slightly less as compared to the copper. On while with the increase of the temperature, both are going trends are the same. The diffusion rate is going to increase with the increase of the temperature. This one is actually the copper on silver. We can those cases were actually homogeneous, while this is the heterogeneous case. Their copper on the silver one surface, and the copper actually here also showing the same attitude with the increase of the temperature. We saw over here that the trajectory followed by the center of mass is going to increase with the increase of temperature. It means that the diffusion rate is going to increase with the increase of temperature. While it means there are a number of types of the processes right now involved in the diffusion process. Now we can give some reason why these are the different behavior. Both three cases, two for the homogeneous and one for the heterogeneous, are showing some different attitudes. Actually, copper and silver. In case of the copper, the copper radius atom size is 30, almost 30% less than the silver. These are the energetic. These are the that's why copper's diffusion is relatively high as compared to the silver one. While on the other side, when we take the heterogeneous case, copper silver, then the copper silver have the bond length variation almost into 27 to 30% variation, and that's why the all competition between the atoms to get minimum energy configurations a little bit high, and that's why the diffusion rate is going to increase. This is the diffusion coefficient for the all. Actually, I represented over here only one island's story. While for all islands, we saw over here that from 1 to n atoms, with the increase of the island size, we have seen that the diffusion rate is going to decrease. These diffusion coefficients are actually at 300 Kelvin, 500 Kelvin, and the 700 Kelvin. So then we can say that with the increase of the island size, the diffusion is a little bit difficult because now the mass is going to increase, and the more energy is required, which is actually provided by the dynamics of the lower layer substrate atoms. This is RNS plot, and this is providing the energy barriers and the attempting frequencies, how they are going to take some steps which are frequently involved in the surface diffusion. This is the effective energy barrier. Effective energy barrier we have compared with experimental ones, and we saw over here that the effective energy barriers are very near to the experimentals and the other theoretical results which were taken by the Monte Carlo and the density function theory. Our results are very good and in the range of the experiments. Processes, number of processes observed in the surface diffusion, hoping the change of the position of the atoms from one energy minima to another energy minima on the surfaces. We have some idea about the surfaces. You people have, if we consider the one surface of FCC that carry some energy minimas, and atoms should sight on the minimum energies, not on the maximum energies. So there required some energy barriers to go to the next energy minima. To do this one, it has to face the hopping process and the pop-up knocking out of one atom from the surface of the crystal, normally in the upward direction, and anchoring. If one peripheral atom changes its position and regain its original position again and again, that is anchoring. And the breathing atoms of an atom tends to move but not able to change its positions practically. This is actually that is trying to do, and the shearing, sliding of only one line of atoms along the other line of atoms on the surface of the crystal, that is shearing. And the concerted motion, if the whole island of the atoms changes its position from one place to another place collectively, that is known as the concerted motion. These all steps are actually part of the surface diffusion. Sometimes they only one atom, single atom, two atoms, and then sometimes the many number of atoms are involved during the diffusion. No doubt, at for the large islands, the only peripheral atoms are the part of the dynamics, while the inner ones are maybe on the other word we can say the static. But with the increase of the temperature, they all followed the dynamics. Diffusion parameters for the 1 to 9 atoms copper on the silver one. These are the parameters. These are the actually diffusion coefficients at 300, 500, at 700 kelvins. That we have calculated the energy barriers. We saw over here that the energy barrier is going to increase with the increase of the island size, because there is required push energy high as compared to the lower one, which is very small in case of the monomer, which is very aggressively move on the surfaces. Diffusion prefactor, which is actually providing the attempting frequencies, and these are the parameters, and which provide the all story of the diffusions of the surfaces for the islands. Copper trimer behavior at the silver one surface. We have saw over that in the presence of the copper, there are some fissures and dislocations. 10 true dislocations are appearing on the surfaces due to the weight of the island. And on the other story, we can say that here the copper silver bondings are overcome on the silver bondings, and that's why the silver atoms a little bit stretch towards the island. And we saw that there are some fissures very near to the, which are near to 2 angstrom to the island, and 2.5 angstrom dislocations are appearing. And the lower one picture actually representing some vacancy formation. There red colored are actually island atoms, while the blue colored atoms are the substrate atoms, which is silver over here. Here we saw that with the increase of the temperature at 700 Kelvin, the substrate atom popped up, means the surface atom becomes absorbed atom, becomes a part of the island. This is indigo color actually representing here, which was the part of the surface, and now it is popped up, and now it can move on the surface, and it is not the part of the crystal right now. But during the diffusion, we saw with some passage of time, one atom of the copper absorbed in the surface, which is representing by the last picture, which is with the green color here. This atom take the position of the surface and becomes the part of the surface. And now the absorbed cluster here, 3 atoms are not the same type of atoms, 2 copper and 1 is the silver, which can move on the surface. They can move, but we saw over here that the copper atom size was less than the silver. That's why there remains some lapse well over there. Already this is the well which is created by the vacancy formation, by being a atom pop up knocked from the surface. Then other one atom which was the part of the island now becomes the part of the surface, which is representing by the green color here. Remaining some lapse well over here, because the size of the copper is less than the size of the silver. Due to the lapse well, this island remains stick to that well, because there is some kink for the island, it's difficult for the island to move from that position. So at very high temperature, it moves from that one. No doubt, it moves. However, it stick for a time, almost 40 to 50 picosecond on that position where it makes some exchange of the substrate atoms with the island atom. We also saw that the migration of the vacancy here, left one actually representing the rectangles, actually representing the dislocations, while the circles are representing the fissures. We can saw here the migration of the vacancy, the yellow colored atom, which is right side of the in left picture, and the right one we can see this is on the top and the left side. Right picture, that yellow colored become changes the position. This yellow colored atom actually makes some sense of migration of the vacancy. And the popped atom is now indigo color is lower one. We saw that with the passage of the time, this is actually in 0.5 picosecond. We saw that the dislocations, we can saw the dislocations are attracting each other. They come closer to each other, while on the other side the fissures, they moved away. And on the other side, we can say that the defects are attracting each other. These dislocations are the normal defects of the crystals, while the fissures are the gaps which developed due to the atomic oscillations. They cannot attract each other. No way. They have to move away each other, while the dislocations are attracting each other. In next slide, this is the snapshot of the ternary, copper, zirconium, silver alloy. This is actually very interesting results. These are three atoms of the species, those combining the cluster, trimer, hexamer, and the nonamer. These are the pictures of the. Hexamer is missing right now. Trimer and nonamer and the decamer. These are the different snapshots, and we saw that there is a formation of the vacancy in second row, and some migration of the vacancy in third picture, and then some migrations, that is atomic diffusions due to the island. On the other side, we saw without these islands, there is no this type of the defects. These defects are that actually it is due to the weight of the island and the forces between the host and the guest atoms. And these actually host guest atoms, the bondings overlapped on overcome on the bulk bondings, and that pull the atoms from the surfaces. And we saw that these make some inharmonicity. These create some disturbances on the surfaces. These change some fields on the surfaces. And we also saw some exchange of atoms. Blue colored atoms are actually right now in part of the island. This is the atomic exchange process here, which was seen in the previous one, how surface silver atom becomes part of the island, while on the other side the island atom becomes part of the surface. Here actually zirconium atom is too energetic in this one, which is a lighter one, and it's so mobile, and it becomes part of the surface, and atomic exchange process is just represented here. These are blue colored atoms are actually the surface atoms, while the I atom, which is the surface atom, how it gets the position of the surface, and the surface atom K, which is going to pop up. This is the whole story of the atomic exchange process.